Hi children, hopefully you are doing well in your preparation, and in this session I am going to cover one of the important topics like ray optics, and welcome to you all to the Sri Chaitanya's prestigious NEET Sankalp 2.0 program. And then we will start the topic here. You know, ray optics is a very big topic. First a few instructions here, and I will do the concept, and accordingly that problems will be covered, and some of the model problems I will explain. The other problems which I am showing here, you please check that solutions, and you can pause the video and you can try. Is it clear? Right. So today we will start that now the ray optics here, and in the ray optics, children, you know what are the areas that we are going to cover in the ray optics. Majorly that we have about ray optics, we have a certain important the properties that we have about the reflection, we see that, a refraction we see, and in the refraction of course different applications that we have here, and at last the dispersion, right. So majorly the reflection, refraction are the major areas that you are normally observing in the different competitive examinations. Is it clear? And in the today's session, first I will cover some of the theory concepts, and I choose some of the questions which are related with the previous NEET questions and other competitive examinations, right, which are also expected for this weekend, right. So now we will see in the reflection. First we will start that in the ray optics, first we will start that reflection, and see that reflection plane mirrors, next spherical mirrors, we will see that. Basically in the reflection you can see what is exactly the reflection is. Whenever the light energy made to incident on a smooth polished surface bounce back into the same medium, there are certain laws in the part of reflection. Is it clear? So now if you see that here, the laws of reflection, if you see that here, laws of reflection, if you see, very simple laws here. Whenever any particular reflector, this is called the plane reflector, this is called the spherical reflector. In the spherical reflector, this is called a concave reflector, also called as a concave mirror. This is a concave mirror. If you take that a convex reflector, this is a convex reflector or convex mirror, we say that this is a convex mirror we call, where the bulging side is a reflector, and a concave mirror, this is nothing but what actually depressed side is a reflector. Okay. Now let us take that here. For this a center of curvature will be there, for this center of curvature will be there, for this radius of curvature will be a finite value, radius of curvature is a finite value. Let me take that here, this is called the radius of curvature, this is a point on the principal axis, I mean on the mirror, center of the mirror, and it is called the pole, and this is a center of curvature, this is a center of curvature, this is a pole, right. So this is a line joining these 2 points said to be the what actually the normal. Is it clear, children? So this is how the normal, the role of the normal in the optics is very important in both reflection and refraction. Let us take that here. In this case, for this, where is the normal? Normal you can imagine in case of plane mirror immediately, but in case of the spherical mirror, what actually here, you should take the center of curvature. Okay, right. So in this case, as it is a normal here, in the normal, the ray which is striking here at a certain angle, this is called the angle of incidence, and the angle of incidence and angle of reflection will be equal in magnitude always, either side of normal. This is the angle of reflection is equal to angle of incidence. Now the ray which is supposed to go like this get deviated by this amount, this is called the angle of deviation. Angle of deviation will be equal to what actually here, 180 degrees minus sum of these two. You all know that here R is equal to I in case of any kind of reflector. Even in case of the spherical reflector, the ray which is striking here at an angle and gets reflected at the same angle, R is equal to I. And in this case also, the ray which strikes here gets reflected, and angle of incidence, angle of reflection, which is equal to angle of incidence. So this how we can say, in every reflector, whether it is a spherical reflector or a plane reflector, angle of deviation, only one formula that we have here, angle of deviation is equal to pi minus 2i or pi minus 2r, because r is equal to I, because you know that this total angle is a pi and which is equal to I. So this is what actually about the first one. In the laws of reflection, incident ray, reflected ray always at either side of the normal, Angle of reflection is equal to angle of incidence. A simple concept about this. Now, in case of plane mirror, one or two simple questions we will see that. About the plane mirror, if you see here, basically we are going to discuss about the plane mirror and spherical mirror separately. Now, first we will see that about the plane mirror, children. In case of plane mirror, always remember with respect to the mirror, the distance of object is always equal to distance of image. The image formed by the plane mirror always, because very well known, regularly you see the plane mirror, the image formed by the plane mirror is always like virtual, same size, erect, laterally inverted we say at either side of, because virtual image always will be behind the mirror. In case of lenses it will be different, later we will discuss. In the mirrors, virtual image always behind the mirror, point to be noted. Now, in this case what actually you can see in case of plane mirror, if at all the object is here, the image will be here. How the image will be here? Because the rays which are striking here gets reflected like this. So, the image will be formed here, and therefore, the distance of image is equal to distance of object, right. Always with respect to the mirror, even if the object is moving or mirror is moving, whatever it is, both are moving, always you remember the distance of object with respect to the mirror is always equal to the distance of the image with respect to mirror at the same distance. Is it clear? So, the position of image, position of object with the mirror always will be equal, and both are at either side of the mirror. Okay. In case of plane mirror only I am discussing about this. It always form the virtual same size. Is it clear? And all the mirrors will form the virtual, but plane mirror always form the virtual image for the real object, point to be noted. Plane mirror also can form the real image, but for a virtual object we have one question we will discuss there, right. So, coming to the point here, and spherical mirrors also will see that. In the spherical mirrors, children, and just we see that first concave mirror we see that. In case of concave mirror, how the image and all you know that, and first of all you must know the mirror. You please once check that the textbook about the position of images. This is a focus and this is a center of curvature, this is a pole, right. So, in case of spherical mirrors, that too concave mirror can form real image as well as a virtual image. If at all object is at infinity, the first object at infinity, let us assume, where will be the image? Where will be the image? Image at focus, the I1 will be at focus, because rays coming from infinity after passing through the, after striking the mirror, they converge at the focus. Whereas in case of convex mirror, in case of convex mirror here, and the rays which are striking here, same, the 3 points to be noted. First of all, center of curvature, focus and a pole, and the rays which are coming from the object at infinity, the rays are parallel to each other. Here is also the object at infinity, the rays coming from here. After striking this, the rays converges, and hence concave mirror can also be called as converging mirror. Lens is reverse, right. So, the rays will converge at this place, and where the rays are reflecting, rays are converging, that point is said to be the real image point, and the real image is at focus. And in this case you see the rays appears to diverge from the point on the principal axis. This point is said to be the focus, and this is said to be the focal length, and this is said to be the radius of curvature. Is it clear? So, for the different positions of object we can see the different positions of images, and all. It can form the real magnified image whenever the object is real magnified image, real diminished image, and virtual magnified image. It always form the real image magnified, real image same size also possible, real image small size also, diminished image also is possible, but it can form the virtual image. Only one kind of virtual image is formed, which is a magnified virtual image is formed. If at all in the question, and a mirror forming a virtual image of 2 times the size of the object, that is a magnified image, indirectly it is a concave mirror. Plane mirror always form the same size of image. Convex mirror form the virtual image only, for real objects I am talking about. Is it clear? And it can form the virtual image, always diminished virtual image. And wherever the image which is formed at the focus, which is a very small virtual image, is a virtual image which is a very small virtual image. Is it clear? And depends upon the position of object, the images changes, right? Now, what are the important relations in case of mirrors, children? What are the important relations? And in case of mirrors, the relations here, if you see here, first one is relation between F, U, V, and the relation between F and R. If you see that here, first F and R relation, you can see that only for a mirror, spherical mirrors here, R is always equal to twice to the focal length. Radius of curvature is almost twice to the focal length, approximately. And the second one, in case of mirrors, it will be different from the lenses. In the lenses, it will be different. And the focal length of mirror depends upon only on radius of curvature. It never depends upon the nature of material of the lens. Whether the material is of glass or diamond or a graphite, doesn't matter. Always depends upon the radius of curvature in case of mirrors. Now, and the next relation, UVF relation, 1 by F is equal to 1 by V plus 1 by U, where V is the distance of image, U is the distance of object. Now, third one here, in this case size, how much it increased, that is called the magnification, magnifying power, we can say that, height of image by height of object, and that is equal to minus V by U in case of mirrors. Majorly these are the three important relations, majorly three important. I am going to cover the major very important points only I am going to cover here. In this case, M is equal to height of image by height of object, and which is equal to minus V by U. Even with the speed and other things also we have some question and we will discuss, right. So, this is about the relation for mirrors. Now, let us take that here. In this case, what are the sign conventions, children? Sign conventions are very important whenever you take any distance in the direction of incident ray. Sign conventions I am writing here, whether mirrors or lenses, sign conventions. Incident direction, whenever you take that any distance in the direction of incident ray, positive. Any distance we measure opposite to incident ray to be taken as negative, distance negative. And the next one, and size of image or object, any size and vertically upward erect, which is said to be the positive, and the size which is inverted always to be taken as negative. That is the reason we can say that here, in case of concave mirrors, or in case of any kind of the mirror here, whenever you are getting the real images are always inverted. Therefore, magnification for the real image is negative, point to be noted. And virtual images are always positive, because virtual image always will be erect, is always positive. Okay. Now, coming to the point here of some problems related with the mirrors, we will see the children. And in the mirrors, plane mirror, spherical mirrors, the two parts under the reflection. Now, coming to the point here, problems. And one of the point you can see that it is desired to take the photograph of the image of object placed at distance 3 meter from the plane mirror, children. And this is a plane mirror. Object placed at distance 3 meter from the plane mirror. This is the object which is placed at 3 meter from here, 3 meter from here. So, in this case, and the camera which is at a distance of 4.5 meter from the mirror should be focused for a distance, what actually here in this case, because you see that here, where will be the image, because you see that here, and which is at a distance of 4.5 meter from the mirror. This is a camera position, this is a camera position here, camera is here, he wants to take the image, he wanted to catch the image here, who is at a distance of 4.5 meter. So, definitely you know that here image also will be at the same distance as that of object, which is equal to 3 meter, children. Therefore, from here to here, at what distance here? 7.5 meters. That means a cameraman has to focus the image at a distance 7.5 meter, right. Now, we will see that the next point, children. Two plane mirrors are inclined at 70 degrees. A ray incident on one mirror at an angle theta After the reflection falls on the second mirror and reflected from the parallel to the first mirror, the value of theta to be find out here in this case. Now you can see children, these are the two mirrors here, the mirror 1, mirror 2 in this case, and you can see that here what exactly mentioned, the mirrors are inclined at an angle 70 degrees. Ray is striking at an angle theta, ray is striking on one mirror at an angle theta here in this case at an angle theta, gets reflected the same angle as angle of reflection is equal to angle of incidence. Is it clear? So definitely it go, and after the reflection he said very clearly, reflected ray comes out parallel to the first mirror. This is the first mirror, the reflected final reflected ray coming out parallel to the first mirror. Therefore, this is 70, definitely this angle also will be equal to 70, this is also equal to 70, as is 70 this is also equal to 70. You know, this is 70 and 70, definitely this must be 40 because sum of the three angles in a triangle 180. So we can say that exactly which is equal to, we got that 40 here. Once it is a 40 children, this is also equal to 40, this is also equal to 40, 20 and 20, because see that here this one and this one are 40, this is a normal here, the ray will be reflected at an angle 20 degrees and definitely the reflected angle is also 20 degrees, therefore this total angle is equal to 40. So the answer will be equal to what actual theta to be find out, because the 40 and the total angle is 90, and definitely this must be equal to 50, the angle of incidence is equal to 50 degrees here. Now the first option is correct. Now let us go for the next one. An object is placed at a distance of 40 centimeter from the concave mirror and a focal length 15 centimeter. Object is displaced through a distance of 20 centimeter towards the mirror. The displacement of the image will be equal to what actually? In this case you can see, first of all, what is the position of the image, first we need to calculate, that is the V1, and what is the distance of image in the second case also we need to calculate. So for the first one you can see that in the first case you can see, first what is saying that here this is a concave mirror, simple calculations I am leaving to you the calculations here. Object was at distance of 20 centimeter first, 40 centimeter, this is the first position of object, which is the distance of 40 centimeter children, 40 centimeter. So where will be the image, because you know that here the focal length of this mirror is equal to only 15 centimeters and radius of curvature is here, center of curvature, it is beyond the center of curvature. So therefore what actually here the image will be a diminished image, because object is beyond the center of curvature, the first image will be here, I1 will be here. You need to calculate this distance V1, and with what formula you can apply here, you can apply here U1 is equal to minus 40, you can take that, F is equal to, you take it as minus 15. So you can calculate from this V1, you can calculate, substitute. Then after the second case what is saying that here object is displaced through 20 centimeter towards the mirror. Once object is moved towards the mirror, earlier object was here, now towards the mirror by 20 centimeter, now object comes to between the center of curvature and the focus, center of curvature, this first position of object, this second position of object, the image will be shifted to this side here. Earlier image and this image you can see that first image is between F and C, because object was beyond center of curvature and image was within the between center of curvature and focus, and in this case when object comes to the between F and C and image goes beyond, this is the image distance here. Second case, first image distance is known, second image distance you can calculate from this, because here object distance is you just substitute V2, U2 is equal to minus 20, because this is a 20 centimeter, and focal length is also given minus 15 by the sign conventions to the left side, and you can calculate V2. After finding V2 children, you can find out the shift is equal to V1 minus V2 or V2 minus V1, right. So this is about spherical mirror, one of the important model here. Next, object placed at a distance equal to focal length of convex mirror. The focal length of the mirror is also F is given. What is the distance of image from the pole of the mirror, right. So let us take that here. There is spherical mirror, convex mirror, the focal length of this one is equal to F only is given, and this is a focus, and object is placed children here, very clearly given, object is placed at a distance equal to in front of this at a distance equal to focal length only is given, then image will be, because in the last slide I told you already, whenever the object is at infinity, image is at focus in case of convex mirror. If object come closer to the mirror, then what actually here, image slowly move towards the mirror. It always form the virtual image, I told you, it always form the diminished image, and also I told you the image formed by the convex mirror always between the F and pole, right. So, the image will be formed here only. How do you calculate this image distance? We can see that here a simple relation that we have here, 1 by V plus 1 by U is equal to 1 by F, children. And is the focal length is positive or negative? Focal length is positive, because incident ray is this. Incident ray is this, and this is the object distance, and this is a focal length. Focal length is positive in case of convex mirror, because focus is this side, concave mirror reverse, and here 1 by V to be find out here plus 1 by U. U is equal to how much, children? Here U is equal to focus but negative side, and this is positive only. So, therefore, 1 by V is equal to 2 by F. So, V is equal to F by 2. Very simple way we can write it. Is it clear? Less than that of focal length. Image formed by the convex mirror always within the focus only, always virtual for a real objects. Is it clear? Now, that is all about the mirror concepts. Now, we will go to the next. So, once again I am telling you, wherever you want to see the problem thoroughly, you just pause the video and check that. Now, we will see that refraction, critical angle, total internal reflection, all at one stretch we will see that. Okay. Now, refraction says whenever the light go from one medium to another medium, it undergoes change in direction, change in speed, change in wavelength. Such phenomenon is said to be the simple way of refraction. And how that wavelength changes, how the speed changes, and how the direction changes, let us see that very simple relation that we have. Is the refraction depends upon only one medium? No, it depends upon both the medium, incident medium and refractive medium. So, how that both the medium and which physical quantity is estimating the both the medium is, that is called the refractive index. Okay. Now, let us take that here, whenever the ray, only one diagram you can see that for the refraction totally. This is a medium 1, medium 2, the ray which is striking, here at an angle of incidence, I will take the theta 1, I take it. Let me take that the ray supposed to go like this, I am taking like this, it goes like this. In what direction, that is a different thing. This is an angle theta 2. In the first medium theta 1, second medium theta 2, normally we take it as the angle of incidence I, this is R, I am not using that. And here the speed of the light is equal to C1, speed of the light C2, wavelength of light in the first medium lambda 1, wavelength of light medium lambda 2. So, these are the three physical quantities which are affected by the refraction. Now, how much it affected? We can say that here refractive index of medium 2 with respect to medium 1, with respect to medium 1. How to write? You know, this is the one we write it, that is equal to mu 2 by mu 1. Children, you try to understand here, very important point here, speed of the light inversely proportional refractive index, more the refractive index less the speed, and wavelength of this is inversely proportional mu, sin theta also inversely proportional mu. These are the three physical quantities are inversely proportional mu here. Therefore, mu 2 with respect to 1 is equal to mu 2 by mu 1, which is equal to C1 by C2 lambda 1 by lambda 2. This is one of the most important formulae, many questions that you can expect only from this formulae in the refraction. Now, coming to the point, next one, and one example I will tell you here, after this I will give that, and a total internal reflection and critical angle, this is another concept in this, and this is one of the application of refraction we can say. Whenever the ray goes from, this is a denser medium I will take it, and this is a rarer medium, this is a normal, and the ray which strikes from a denser medium, let us assume that here ray is striking at a certain angle of incidence, the ray will be refracted along the interface of the two medium that is angle of refraction is equal to 90 degrees. This is called the critical angle. Critical angle is the angle of incidence at which the angle of refraction is equal to 90 degrees, and we have a simple relation for this. What is the refractive index and other things? If at all if I less than that of critical angle, for a given medium critical angle is something will be there, some constant will be there. For example, if you take a pure glass with respect to air, refractive index is equal to 1.5. Critical angle for the glass is approximately 42 degrees, and for the different medium it will be different here. And is the critical angle depends upon only one medium? No, as the refractive index is depends upon the two medium, and definitely what actually here also. Now let us take that here, if I is less than that of C, then the what actually here, ray undergoes refraction. Refraction takes place. If I is equal to C, critical refraction, this is a critical refraction. Next, I greater than C, it undergoes total internal reflection. Is it clear? So now we can see in this case what is exactly another formula of the refractive index of denser medium with respect to rarer of a given pair. Denser with respect to rarer of a given pair is equal to 1 by sin C. This is one of the most important formulae in this case. So this is about the critical angle and total internal reflection. We have a certain applications, we will see that here. Now coming to the what are the other formulae also, we can see that. See children, a mark is made at the bottom of the vessel, and over this mark a glass slab of thickness 3.5 centimeter and the refractive index is 7/4 is placed. Now the water is poured onto the vessel so that the water surface is 8 centimeter above the upper surface of the slab. Looking down normally through water, the apparent depth of the mark below the surface of the water. So let us take that here. There is a vessel, there is a glass, and a glass here, and he is saying that here glass slab of thickness 3.5 centimeter, and over that there is a water which is 8 centimeter above the surface of the slab. Looking down normally through the water, apparent depth of the mark is equal to what? And for this one more formula here we can say refractive index, one formula with the critical angle we discuss, refractive index is equal to denser medium to the rarer medium or rarer medium to denser is also. I am taking that here real depth, our case here real depth by apparent depth. Whenever object is in, when object in denser, when object in the denser medium, simply we can say that here real depth by apparent depth. So let us take that here real depth is what? Real depth is 3.5 and 8 centimeter. These two are the two different medium. This is a mu of glass and the mu of liquid. Accordingly we can write it as real depth by, we get apparent depth is equal to what? We can write it, please children, and apparent depth is equal to, from that we can write as real depth by refractive index. Real depth in the first case is equal to 3.5 by 7/5 is the refractive index, plus next one is 8 by 4/3. If you do that exactly you get that 8 centimeter. Actually the really is at what distance? 11.5 centimeters, appears to be at 8 centimeters only. Is it clear? Now let us go for the next question. See, a point source of light is kept at a depth h in a water, a refractive index is equal to 4/3. The maximum radius of the circle at the surface of the water through which a light emits. See children, this is one of the important applications in the critical angle and refraction children. And you see that here water refractive index is 4/3, and you can see the point object is kept at depth equal to h. A point object is kept at a depth of h. The rays coming from here goes like this here. Then what about before? This ray will come out like this, safely come out. It undergoes refraction. This angle is equal to critical angle. this angle is equal to critical angle, because this ray is striking at an angle, critical angle, the ray will be just refracted. Now at this angle you can see that here, at this surface here, this particular ray will be undergoing total internal reflection. This also undergoing total internal reflection. So he is asking that here maximum radius of the circle through which the light comes out. This is only that the radius of this one through which the light is coming out. This is a area where the light undergoes the reflection. Here is also undergoing the reflection. This is the area through which that comes out, and this is equal to the radius of the circle. And how to find out the radius of the circle? From this triangle you can see, this triangle I am taking here. This is a radius R, and of course this side is also R, and this is equal to H, you know. This angle is equal to critical angle. Tan C is equal to, we can say that R by H. So R is equal to H tan C, right. So whatever the values are given, accordingly you can take that here. Refractive index is given, and once the refractive index is given, how to calculate here? Tan C, you know, sin C is equal to 1 by mu, you know that here, 1 by mu. Then this is equal to under root of mu square minus 1, you know, from the Pythagoras theorem we can apply. Tan C is equal to what? Tan is opposite by adjacent side. Tan C we can calculate, children, which is equal to 1 by under root of mu square minus 1, and mu value is given as 4 by 3. You can substitute, you can find out the tan C, and you can substitute in the final answer. You get that answer is equal to 3 by root 7, right. Now let us take that the next question. Refractive index of medium is mu. Incident angle is twice that of the refracting angle. The angle of incidence is equal to what? I told you already, the first formula is very important, and in this case you can see here, refractive index of medium is given, angle of incidence is twice to this. First of all you must write that twice to the angle of refraction, but is asking that here angle of incidence. Therefore you need to eliminate R. R is equal to I by 2. Now we will go for the formula, a simple formula that we have here. Mu is equal to, from the Snell's law we can also say that here, sin. And if you substitute, children, we require I, therefore R to be eliminated, you must see that, and in this case R is equal to I by 2, sin I by 2. So since I to be cancelled here, part of it, and this we can also write here 2 sin I by 2 cos I by 2. From the trigonometric relation, you know, sin theta is equal to 2 sin theta by 2 cos theta by 2. From that we can find out here, these two can be eliminated, and from this cos I by 2 is equal to mu by 2. Therefore I by 2 is equal to cos inverse mu by 2, and this 2 goes to that side. I is equal to 2 cos inverse mu by 2, right, children. So this is a one. Now there are some other models, you can check that and you can do that wherever you want, because I gave the solutions. You can pause the video and you can check that. The next immediately after this, refraction. This is also similar kind of question, you can check that. This is also similar, air bubble inside the glass, same thing, the same concept here. And this also just now we discussed similar kind of model, and I gave the complete solutions. Please check that and video pause and you check that once. This is the one already we discussed. Light ray travels to medium A and B, speeds are given, speed in the first medium is given, speed in the second medium is given, critical angle is asking. For finding of critical angle, you know, refractive index of denser medium with respect to rarer medium is required. So for this you see mu 2 by mu 4 or mu 1, I write it, which is equal to V1 by V2 substituted, and we are going to get that here mu 2 by mu 1 is equal to, this is a denser medium, second medium is denser with respect to the first, that is the reason mu 2 by mu 1, directly we can write it. Next, refraction of the single spherical surface. Before going to the lenses, you need to have this particular one. Till now we discussed refraction of the plane surfaces. Now refraction of the single spherical surface. If at all one surface is like this, till now we did refraction at the plane surface. Now refraction, if at all a glass is like this spherical surface, this has the center of curvature, because every surface will have some like this, and this has the center of curvature. This is a medium completely. Let us take the glass, and this is air medium. or anything. This may be a glass, this may be air, you can apply anything. So, I will take that here. This I am taking as a first medium, incident medium, this is a second medium. Whenever the object is placed in front of it at a distance u, let us take that image will be formed here at distance v. Then what is the relation between the uv? Already we did in case of mirrors. Relation between the u and v is equal to 1 by v plus 1 by u is equal to 1 by f in that case. Now in case of refraction at the plane, single spherical surface, we go for this mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r, where mu2 and mu1 will be given. Accordingly, you can calculate. In our question very clearly is given, radius of curvature is given 30 centimeter. Is it the plus 30 minus 30? Because this is center of curvature is here. Center of curvature, radius of curvature is positive. Radius of curvature, because object here, the rays are striking like this, incident ray is like this, incident ray. This object distance is negative and radius of curvature is positive. R is equal to plus 30, u is equal to minus 15 and mu1 is given, it is air medium 1, mu2 is equal to and a glass medium which is equal to 1.5. You can substitute here, you are going to get answer exactly 30 centimeters, you are going to get it. If at all you get the positive 30 centimeter, image will be to the right. If at all you get the image to the left, you get a negative answer. So, I think we get that answer negative, therefore, minus 30 centimeters. You can verify and check that. Okay. Next, lenses children. In the lenses, this time also one important question has come and expecting many questions from this particular concept here. Now, lenses, we have a different kind of the lenses that we have here, and this is a biconvex lens. If at all both the curvatures are same, equiconvex lens. This is a biconcave lens. This is called the plano-convex lens. This is called the plano-concave lens, and a convexo-concave, concavo-convex, either way we can say. Like we have a different kinds of lenses, and depends upon the radius of curvature, whether equi or unequal, we can calculate here. So, in this case, if you see what exactly the relations that we have in this case. First of all, in case of the lenses, you take the biconvex lens children, biconvex lens, and it will have a two curvatures. This is a radius of curvature R1, radius of curvature R2. If you can imagine like this is the center of curvature of the first surface, radius of curvature, center of curvature of the second surface, you can take it, and this is the center of the lens called optic center. And though it has a two different curvatures here, and the radius of curvature can be equal or unequal, but for a given lens, whether R1 is equal to R2, R1 is not equal to R2, maybe plano-convex lens, plano-concave lens or convexo-concave, anything, for a given lens only one focal point will be there here, the focal length will be only one. So, the focal length is equal to f and radius of curvature and other relations will see that. And this is said to be the converging lens, because rays which are striking here, the rays will converge. This is a converging lens, and in this case the rays coming from here get diverge. This is a diverging lens, also called as a concave lens, and a plano-convex lens also the same converging lens. But what is the difference between this and this in the sense, if at all you cut a lens into the different parts, what happens, we will see that. Let us take that here. A lens of focal length f, it has a power will be there, and I will give you all the relations, and focal length and power we have here. If at all you cut the lens into the two parts, the focal length of this one becomes what, actually 2f, power become half, because power and focal length are reciprocals. You cannot cut into number of parts here, only the two symmetrical part. But if you cut a lens into two parts perpendicular to the axis, this is the axis of course, and you can see that here in this case, then what happens, if you cut like this, you are going to get the two convex lenses only. In this case, two plano-convex lenses are forming here, and focal length remains same, power remains same, only thing is the brightness of the image changes, right. Even if you cut into the number of parts, also the same thing, focal length remains same. If you cut into number of parts here, focal length of each part will be the same as original focal length, power also the same thing, right. This is one of the important point here. Now, we will go to the what are the relations that we have in the lenses. Relations. This is about the lenses, children. Now, we will see that what are the relations here we have. First relation, same thing, we have a focal length and a radius of curvature relation, children. What is that you can see? This is for a lens, radius of curvature of this one is R1, this is R2, and what is the focal length of this one to be calculated. So, remember 1 by f is equal to mu minus 1 into 1 by R1 minus 1 by R2. Sign conventions to be taken accordingly. Whether radius of curvature is a positive or negative depends upon the kind of the lens. In case of biconvex lens, radius of curvature of this one, if rays are incidenting like this, R1 is positive because center of curvature will be this side. And if at all you take that here this surface and radius of curvature will be negative, this radius of curvature is negative and this is equal to positive radius of curvature, accordingly we can take it. So, we will choose that one question, I will explain. Now, the second question, second formula, f uv relation, focal length u, f u and v relation here, what exactly? 1 by f is equal to 1 by v minus 1 by u in case of lenses, in case of mirrors plus, okay, and image distance, object distance and other things. Now, coming to the third one, same magnification is equal to height of image by height of object, which is equal to v by u. There it was minus v by u. In addition to this, we have some more relations, we can write it as fourth one, power also can be written. Power is equal to power of the lens, refractive power we can call it as. Refractive power is equal to 1 by focal length when focal length is to be taken mirrors in meters, and the power of the mirror is power of the lens is equal to diopters. Is it clear? So, the next one is combination of the lenses. If at all the two lenses, three lenses are kept in contact, and what will be the combined focal length here? Combined focal length. If at all the two lenses, three lenses are kept like this, and combined focal length is equal to 1 by combined focal length is equal to 1 by f1 plus 1 by f2 and so on. Power will be power of the combination is equal to p1 plus p2 plus p3. These are the most common relations, children, and I am going to do that problems based on this. Once check that all the formulae and sign conventions in the ray optics, very important, and ray optics majorly reflection refraction only, dispersion they are not asking much questions. Now, you see in the lenses one of the problem we will see that here, a simple question I will give it to you. Let us take that here, there is a lens of focal length 10 centimeter and the object is placed here at a distance 40 centimeter, and what is the distance of image, this object, what is the distance of image I want to take that, and the size of object is also is given, size of object is 2 centimeter, what is the distance of image? To be find out here, first of all we need to find out the image distance, and simple question here, see what is the relation, the first point is I want to find out v and also I want to find out the height of image, the two questions are there here. For this first 1 by f is equal to 1 by v minus 1 by u. Okay. So, you take that focal length is positive or negative. Remember, for a convex lens focal length is positive, for a concave lens focal length is negative. Convex lens focal length is positive, concave lens focal length is negative, right. If the rays are converging, focal length is positive, remember. And even in the mirrors, convex mirror focal length is positive, same, concave is negative, remember concave focal length is always negative whether mirror or lens. You can write it on the notes also, like for a convex focal length is always positive whether mirror or lens. So, focal length is equal to here how much we will see that, which is given as 10 centimeter, 1 by v to be find out, 1 by u, u is to be taken negative because we are taking the incident ray like this, rays are striking, incident ray is like this, which is equal to minus 40, you can take that. For this you can say 1 by v is equal to 1 by 10 minus, because minus of minus plus it goes to here 1 by 40. You can say that here, which is equal to 40 minus 10 30 by 400, we can take that here v is equal to 40 by 3, which is 13.33 centimeters. Image is at a distance of 13.33 is a positive. Image distance is positive instance, definitely the image will be to the right side only. Image will be formed here at a distance v. When object distance is here, image is here. Convex lens can form the virtual image, but for an object when it is placed within the focus, right. So, that is how we can find out. Next one children, here magnification we know the formula. Height of image by height of object is equal to v by u, which is equal to v is equal to how much? Plus 40 by 3, and object distance is equal to how much here? Minus 40, which is equal to, we can say that here, and height of image is equal to height of object by 3 minus height of object is equal to 2 centimeter. I gave you 2 by 3 centimeters. This is about the lenses. Okay. This is one of the important one, and we have some questions and you can check that here. See, a convex lens made up of 3 different materials shown in the figure. For a point object is placed on its axis, the number of images formed here. So, these are the 3 different materials he is saying. This is a one material, this is a one material, this is another material. 3 different materials, mu1, mu2, mu3. And refractive index, because focal length depends upon the refractive index, naturally image distance also changes, and how many focal points will be there, how many images are possible instances. And let us take that here, for example, this is a one ray incidenting, this ray 1 incidenting, this is one ray incidenting. Assume that mu1 is greater than mu2 is greater than mu3. When mu is more, refraction is more, this ray will meet here. This image will be the rays coming from here, one more image and one more image, like the 3 images are possible here. Every medium will form its own image. Next, and this is a point you can remember, number of images is equal to number of materials only, number of materials. Even if the lens is kept like this, this is one material of mu1, this material of mu2, even if it is the material of mu1, this is equal to mu2. Here 2 materials only, do not think that 4 materials we have, because this is a mu1, this is a mu1, this is a mu2 and mu2. The 4 different parts are given, and ultimately the rays which are coming from here meet at one place, and the rays which are coming from the mu1 also meet here only. Therefore, because of mu1 only one image will be formed, because of mu2 the 2 images are possible here finally. Okay, the 2 images are possible for the 2 materials. Now, let us take that the next one. A parallel beam of light incident on a system of 2 convex lenses of focal length f1 and f2, or whose focal lengths are given. What should be the distance between the 2 lenses, so that the rays come out as a parallel only, undeviated. The rays coming from here should not get deviated, in the sense definitely they should come out like this. Parallel rays comes out parallel in sense, and the focal length of the combination, remember children, focal length of the combination tends to infinity, because there is no like refraction at all. Ultimately that refraction, whatever the converging part, gets cancelled by this, and finally focal length become infinity, because rays are not being anywhere like converge. In this case, what actually here, what must be the distance between these 2 is asking. For this 2 simple formula I will tell you here. If the 2 convex lenses are placed such that the rays are parallel, coming out of the parallel, you remember like this, and what must be the distance, in the sense f1 plus f2. If at all one is a convex lens, one is a concave lens, the rays are striking here, coming out like this, the distance between them is equal to f1 minus f2. Remember this, directly you can calculate according to our question, f1 plus f2 here, which is equal to 30 centimeters, because both are convex. Next, and a concave lens of mu 1.5 and has the same radius of curvature r, the immersion in a medium of refraction is 1.75, it behave as, and you know refractive index I gave you formula, focal length, how it depends upon this, 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2. You know children, here even if the lens is immersed, then radius of curvature do not change, it remains constant. So, only focal length depends upon this, and 1 by focal length depends upon the instance, focal length of lens in air by focal length lens in liquid is equal to refractive index of material of the lens with respect to the liquid minus 1 material of the lens with respect to the air minus 1. You can substitute directly, you are going to get that here. This is a formula we can find out, right. So, you can substitute and how that image will be formed and all. Next, a convex lens of 40 centimeter is in contact with the concave lens of 25 centimeter, the power of the combination, and one is a convex, one is a concave, you know, one is a convex here, one is a concave, and the focal length of this one is equal to 40 centimeter, f1 is equal to plus 40 and f2 is equal to minus 25, and you can substitute here power, you can calculate from this what is the total power of the combination. You can take that here. How to find out the P1 instance? You know that here P is equal to power of the combination is equal to 1 by focal length. First you can calculate what is the 1 by focal length, otherwise first you can calculate the power. Power is equal to 100 by 40 P1, you are going to get that and substitute. P2 is equal to 100 by minus 25 and you can substitute here, you are going to get that power of the combination that you are going to get it. Next, yeah, a thin symmetric double convex lens has a power P cut into 3 parts A, B, C as shown, and the power of A is equal to what? Power of C is equal to how much? Power of B is equal to how much? I told you already. And when a lens cut like this, power P, the focal length of each part is equal to what actually here? P by 2. Again this cut, power do not change. Power do not change here and power remains same, P by 2 and P by 2 only will be there here. Is it clear? Of cutting also. So, according you can see that here the power of B is equal to only power of this one is asking, power of B is equal to only P by 2. Next, and here a double convex lens has the focal length 25 centimeter, radius of curvature of one surface is double that of the other. Find the radius of, if the refractive index of material of the lens is equal to 1.5, is asking here clearly. Refractive index is given 1.5 and radius of curvature of one is R1 which is equal to R, other one is a twice, he said, other one is a twice. And what is the double convex lens? See the diagram here, radius of curvature of this one is equal to R1 is equal to R, R2 is equal to minus, R2 is equal to minus 2R. And how to find out the radius of curvature? Accordingly we can calculate, because mu value is given, children. Mu is equal to how much is given here? According to this, refractive index of material of the lens is equal to 1.5. So, you can substitute here 1 by focal length is also is given here, which is equal to 25 centimeters. From this you can substitute, I gave that every clear solution here, you can check that R is equal to 37.5. Just only substitutions. See, I am writing again substitution part, mu is equal to 1.5, R1 is equal to plus R and R2 is equal to minus 2R. So, F is equal to plus 25 because the biconvex lens are convex lens only. Okay, children. So, directly you can substitute and you can pause the video and you can check that. Next, and prism. So, in this case, and basically after the refraction we have important topic is of the lenses. The next goes to the prism here. In the prism sector you can see, and simple relation topics only, and I am explaining the concept, you can check that problems thoroughly. And this is a angle between the two refracting surface which is also called as the refracting angle, angle of prism. And let me take that ABC, this is angle of prism, and the ray which is striking here, children, on one of the refracting surface at a certain angle which is called the angle of incidence, and the ray will be refracted. This is a refracted ray, and finally the ray will be emerges. This is the angle of emergence, and these are the points you remember always. What are the important relations? I1 plus I2 is always equal to angle of A plus angle of D. What is angle of D here? The ray is supposed to go like this, get deviated like this finally. This is called the angle of deviation, net deviation, angle of deviation. So, for this what we can say, the next one is R1 plus R2 is equal to A. What are R1 and R2? R1 is the radius of curvature, and angle of refraction at the first surface and the angle of refraction at the second surface, this is equal to R1 and this is equal to R2. R1 plus R2 is always equal to A. Now, how to find out the refractive index? In the sense, we have a different formula here for the refractive index to answer here. Mu is equal to sin I1 by sin R1, Snell's law, or we can also write, children, sin I2 by sin R2. These are the most common refractive index of a prism or any kind of the refracting surfaces. But our concept here is for this you can say, if at all deviation is minimum, because if you see that here ID graph here, angle of incidence and angle of deviation, if you see that here, angle of deviation is not always constant here, it depends upon the angle of incidence. As the I value increases, angle of deviation first decreases then increases at one particular angle of incidence where I1 is equal to I2 deviation and this is equal to I here, but I1 is equal to I2 and the deviation will be minimum here. That minimum deviation at which what actually I1 is equal to I2, R1 is equal to R2. When I1 is equal to I2 and R1 is equal to R2, at which what actually here refracted ray will be symmetrical with respect to base, it will be parallel. Refracted ray, this particular ray is with the parallel to the base of the prism. Whenever refracted ray is parallel, then definitely the angle goes to the minimum, is the minimum deviation here. So therefore, you can say in that case, if at all deviation will be equal to the minimum deviation, for this if at all you substitute here, I1 will be equal to, or I1 and I2 both will be equal to A plus D by 2 and R1 plus R2, R1 is equal to R2 is equal to A by 2. Simply we can write it when the angle of deviation is minimum, right. So from this we have a certain questions, you can check that I gave a thoroughly the solutions and you can check the directly formed relations. I will show that the questions here. You see that angle of incidence and equilateral prism is given, angle of prism is equal to 60 degrees, refractive index √3 and clearly taken that here mu is equal to, because according to this formula we can also write here mu is equal to, at a minimum deviation mu is equal to sin, only remember most of the people will feel that always refractive index of the prism is equal to only this formula. This is only when the deviation is minimum, children. Only when the deviation is minimum we can go for this. If the deviation is not minimum, most common formula of the refractive index is equal to these two. Most common formula, right, depends upon the I1 and I2. Only if I1 is equal to I2, R1 is equal to R2, D will be minimum where the refracted ray is exactly parallel to the base of the prism. Now we will see that directly substitution and equilateral prism, they are parallel is saying. Parallel in sense definitely that minimum deviation case. Minimum deviation directly we can apply sin A plus D by this and angle of deviation calculated from this and we can calculate what is the I. You can substitute. Next, this is also same thing, a beam of monochromatic light incident at an angle 50 degrees on one face of the prism and the angle of emergence is 40. Angle of minimum deviation is equal to how much here? Basically in this case, and I is equal to, for this you can see deviation is equal to I1 plus I2 minus A in this case, and we substituted, children, here I is equal to that and angle of emergence is equal to given as that, and from this deviation is equal to 30. It is not a minimum deviation, this is a deviation for a given angle 50 degrees, angle of emergence is 40. They are not equal. If they are equal, only the deviation is minimum. So therefore for that angle of deviation is 30, in the sense angle of minimum deviation is supposed to be less than that of this, right. The answer will be equal to less than 30. Now other questions based on the same model you can check once. Same direct formulae and substitutions are given, you can check that based on that model. Concept is important and direct substitution. These are the important models as far as the prism is concerned, right. Now the last part that we have here, and we will see optical instruments. Optical instruments, children, a least preferential topic, and most of the times they did not ask the questions, but still you focus on a formula here, just formula based. And here you can see I am showing the diagrams. Simple microscope is a single convex lens which is used for a magnifying purpose, which is called the simple microscope here. And what exactly magnifying power of this simple microscope, we have two different formulae that we have here. what is the magnification, I will show you. I am showing that all things, and angle of deviation, like least distance of distinct vision by the and object distance here. This is the actual formula. This formula can be changed to, if the image is formed at least distance and image is formed at a far distance here, if at all image is formed at least distance of distinct vision, which is called what actually linear adjustment, this is said to be the normal adjustment. Image is formed at infinity and image is formed at least distance of distinct vision. This is called the linear adjustment, which is equal to 1 plus d by f, and this is equal to image formed at infinity is equal to d by f. This is a simple microscope, a single convex lens used to see that magnifying purpose. Sometimes very minute object, very small tiny objects will be there. You cannot see with the ordinary microscope. We go for higher magnification microscope, which is a compound microscope, where we use the two lenses. For one lens we do not get that perfect magnification, you need to get the double magnifier, and hence this is also called as a double magnifier. Magnification of compound microscope is equal to magnification of the first lens into the magnification of the second lens. From this we have a certain formula. I gave that all the formula, once check that here after this. I will show you all the formula here. In this case two lenses we use for this, and object is placed between the f and center of curvature of this one. You can see that here between the f and center of curvature, and the image will be formed here. And what is the, sometimes they are asking what is the nature of this image. It is a magnified inverted real image, image formed by the objective lens, and this is acting as an object to this, then it will form the final image. This is acting as like a simple microscope only, this part, second part. Okay. So for this simple formula base, and what are the formula and all other things, we have a certain formula and we can check that here, and how the image distance and all. One of the formula here, VO by UO into 1 plus D by FE, when image is formed at least distance of distinct vision. This is a linear adjustment we say. Normal adjustment becomes what actually, VO by UO into D by FE. This is equal to normal adjustment. These are the simple microscope and compound microscope, children. The next one is astronomical telescope and terrestrial telescope. Telescope, definitely what actually we see that objects in the space, and where the object is defined already at an infinite distance. Whenever the object is at far, then the rays coming from the object are parallel to each other. They passes through the first lens, which is called the objective. In this case, aperture of the first lens is more than the aperture of this, which is a reverse to the compound microscope, and where the rays coming from here get form the image here, which is a very small image that you cannot see with a direct eye, which is acting as object to the second lens, which is also called as a eyepiece, and it will form the image very close to this, right. So the image formed by this will be, and what exactly the image will be at infinity or at far or at near, we can find out accordingly. Okay. So this is about the astronomical telescope. And astronomical telescope and terrestrial telescope, what is the difference, you know? In case of astronomical telescope, final image is inverted. In case of terrestrial telescope, the image is erect. And what is the reason, what is the behind the science here, in the sense, astronomical bodies, most of the bodies are spherical in shape, does not matter even if the image is inverted. But whenever the object on the space, to see that in the inverted is a discomfort. That is the reason we use that another lens which is called erecting lens. And what this second lens is doing is this, image formed with the first objective will be erected by this, and such that this distance is equal to this one. With this, no magnification, extra magnification, it is only making that image to get erected. So therefore the image of this one will be erected here, and that image again finally we can see with eyepiece. So this is what actually, what is the difference between the astronomical terrestrial, and the magnifying powers are same for both of them, but only the length of the telescope in the second case is more than length of the first one, because we inserted an erecting lens, where the focal length increased by how much it is. You see that here, this focal length is equal to 2f and 2f, and the total distance increases to what actually 4f, and this is equal to image formed by this FO, and this is equal to focal length of this one is FE. Therefore the length of the terrestrial telescope will be equal to FO plus FE plus 4f when image is formed at infinity for a normal adjustment. If the linear adjustment, accordingly, once you see the sheet and you can check that all the formulae what are that. You can check that here all the formulae are given, you can note down, you can pause the video and you can check that all the points are given, very important points, you need to learn all these formulae. Now based on that certain problems are given, that also the solutions are thoroughly is given, please substitute the accordingly the information I am showing here. See that focal length of objective lens and eyepiece are given. Object is placed at 1.5 centimeter away from the objective lens. Final image is at infinity. Magnifying power. Magnifying power of the compound microscope I gave you. Image at infinity is what? Directly substitution only. You can substitute, magnifying power is equal to 200. Okay. Next. And astronomical telescope focal length of objective lens and eyepiece are given. Both are given here. And asking that here, in case of this, final image is formed at least distance of distinct vision. This is called the linear adjustment. In case of linear adjustment, for this magnifying power of telescope is equal to FO by FE into 1 plus FE by D, directly substitutions. FO is given, FE is given, all are, because this is what actually least distance of distinct vision, which is 25 centimeters, and we can find out, children, 30. Next, last two problems here. And a compound microscope of focal length, objective is given and eyepiece also is given, and all are given at final images, you must see that here, final image formed at infinity. For this again magnifying power formula is equal to this. Already I have shown this similar question, you can check that. And this is one question that you need to focus, children, here. And important model, a tube length is nothing but the length of the telescope only, astronomical telescope, which is 105 centimeters, that is FO plus FI is equal to FE is equal to 105, because in this case always the image, object at infinity, image also at infinity. So therefore this distance is equal to FO and this distance is equal to FE, and the total length of the telescope is equal to FO plus FE. Length of the telescope when object is at infinity, image also at infinity, right. So accordingly, next magnification is equal to what? FO by FE. Magnification is equal to FO by FE, right. So magnification we have, length of the telescope we have, and we can calculate FO and FE. FO by FE is equal to 20, FO plus FE is equal to 105, right, children. Next, these are the problems you can check directly. So once again my request, wherever the problems are given, you can pause the video and you can check that solution thoroughly. That is a very essential. Concepts we thoroughly covered and the problems within the time. So to be focused on your numericals. The next one and the last problem is this. Image is formed at a far point here. You can check that up, and focal length of the lens is equal to how much? 5 centimeters. Okay, children. So that's it about the ray optics, which is a very big topic. First concepts you concentrate and formally you focus, whatever that we covered, that's enough. And the problems, what are the models which are required for a NEET, coming NEET, and all the models are covered. You can pause the video and you can check. Right, children? All the best. Bye.